Geometric sequences. Take a moment to complete the lesson opener. See if you can identify the first term and the common multiplier r in each of the sequences. In the first sequence, it's pretty quick to see that the common multiplier is 2. We call this the common ratio r. So I'm multiplying the first term by 2 to get to 6, then multiplying by 2 to get to 12, and so on. Just like with arithmetic, we did term minus previous term to always find that common difference, d. Well, if geometric sequences are multiplying by a common ratio r, if I want to find r quickly, I can take the term and divide by the previous term. So in this case, I could take 6 and divide it by 3 and get 2, or I could take 12 divided by 6 and get 2, and so on. So with that in mind, I could find r in the last sequence by taking 3 to the 8th and dividing by 3 to the 5th. Term divided by previous term. Well, they have the same base, and I'm dividing, so I'd subtract their exponents. 8 minus 3 is 3, so I'd get 3 to the 3rd is my common ratio r. A geometric sequence is a list of numbers with a common ratio r. If I define the first term in my geometric sequence as a, to get to the next term, I would multiply a by the common ratio r. Then to get to the term after that, I would multiply a by r times r. And then to get to the term after that, a times r times r times r, so r cubed, and so on. So to get to the nth term, I would take a and multiply it by r to the n power. We can model geometric sequences in two ways, similar to arithmetic: explicit definition and recursive definition. The recursive definition has two parts, a sub 1 and the general term, a sub n equals r times the previous term, a sub n minus 1. Where n is greater than 1 because we're already given a sub 1. So given this geometric sequence, let's write a recursive definition. R is term divided by previous term, so 12 divided by 4 is 3. Well, let's see if that holds true. The first term is 4, and 4 times 3 is 12. 4 times 3 times 3 is 36. 4 times 3 times 3 times 3 is 108. So for the recursive definition, we have two parts. The first term, a sub 1 equals 4, and the general term, a sub n equals our common ratio 3 times the previous term, a sub n minus 1, where n is greater than 1. So if I wanted to find the sixth term, what would I do? To find the sixth term, I would plug in 6 for n, leaving me with 3 times a sub 5. A sub 5 is 540 because 108 times 3 is 540. So 3 times my fifth term is 2,700. The second way to model a geometric sequence is explicit definition. That's a sub n equals a sub 1 times r to the power of n minus 1 for n greater than or equal to 1. See if you can write the explicit definition for the same sequence. Here, the explicit definition would be a sub n equals 4 times 3 to the power of n minus 1, where n is greater than or equal to 1. Let's verify the first term, a sub 1. When I plug 1 into my explicit definition, I have 4 times 3 to the power of 0. Anything to the power of 0 is 1, so 4 times 1 is 4, which is my first term.
Let's take a moment and practice. Given the first sequence, can you find the recursive definition and the explicit formula, then find out what the 10th term will be? We can see that the common ratio is 2. Term divided by previous term, term divided by previous term. We want to practice that for times when it isn't as simple as multiply by 2. The recursive definition should have your first term, a sub 1 equals 2, and then the general term equals 2 times the previous term. Remember, for all n greater than 1. Explicit, a sub n equals 3 times 2 raised to the power of n minus 1. This formula is good for n greater than or equal to 1. Figuring out a sub 10, I guess we could have continued multiplying by 2, but it seems easier to go into explicit formula. So a sub 10 equals 3 times 2 raised to the 10 minus 1, or 3 times 2 to the 9th. At this point, I'd need a calculator, so I'm just going to leave it there. Let's take a look at our next sequence. Common ratio? 5 divided by 2, 8 divided by 5. I'm not seeing a common ratio. What other type of sequence could this be? Let's see. Term minus previous term. 5 minus 2, well, that's 3. 8 minus 5, that's 3. 11 minus 8, 14 minus 11. This one's arithmetic. Can you remember how to write each of those formulas? It is time to pull it all together. Pause, give this one a try. Okay, I hope you remembered this. So for recursive arithmetic, a sub 1 equals 2, and the general term is equal to the previous term plus 3 for all n greater than 1. Explicit, a sub n equals 2 plus 3 times the quantity n minus 1 for all n greater than or equal to 1. I chose not to simplify it this time. You can, and if I had to use it repeatedly, I would. Now, a sub 10, I just plugged right into explicit formula and got 29. Let's look at our next example. This one has a lot of fractions in it. Can you tell if it's a common ratio? Let's go ahead and try term divided by previous term, but I'm going to start with 1/5. So 1/5 divided by 1/25. Remember, when we're dividing by a fraction, it's the same as multiplying by the reciprocal. So I'll have 1/5 times 25 over 1. 25 divided by 5 is 5. So if this is geometric, then the common ratio is 5. Let's check another one. All right, this checks out. Our common ratio is 5. Take a moment and write the recursive definition explicit and then find a sub 10. Take a look, make sure you have both parts of the recursive definition and the qualifier that n has to be greater than 1, and then the explicit definition. In addition, on a sub 10, you could have stopped right after 1 divided by 625 times 5 to the 9th, but I went a step further. 625 is 5 to the 4th, so 5 to the 9th divided by 5 to the 4th is 5 to the 5th. In a geometric sequence, if we're missing the middle term, we can use the geometric mean. Now this is the square root of the product of the other two terms. Now the geometric mean will always be positive, but we have to keep in mind that because it is a geometric sequence, we might be multiplying by a positive or negative number. We need to look a little further at that sequence to make that determination. So we make sure to note that it could be the geometric mean or its opposite, so just plus minus. Let's try it out. In our example, I added that it's given we have a geometric sequence. Otherwise, we really don't know what the middle term is. The first term is 48, and the third term is 3. If it's geometric, I can find the middle term using that geometric mean. So the square root of 48 times 3. The square root of 48 times 3 is a square root of 144, or 12. But for the missing term, I need to account for the fact that we could have a common ratio that's positive or negative. Looks like we're multiplying by 1/4. Well, 48 times a fourth, or 48 divided by 4, is 12. 12 times a fourth, or 12 divided by 4, is 3. But now let's try it with negative 12. Does it work? 48 times negative 1/4, or 48 divided by negative 4, is negative 12. Negative 12 times negative 1/4 is negative 12 divided by negative 4, positive 3. So there are two possibilities given only the first and third terms. I don't know if it's a positive 12 or a negative 12. Write out the next one. You might want to pull out a calculator. Find the missing term. The geometric mean is 60, and the missing second term could be positive or negative 60 because we don't know what our common ratio is. Well, can I use geometric mean on this last one? No, I'm missing 2 terms this time. So we got to think about what we know about geometric sequences again. I know that I would have to multiply 2 by that common ratio r to get to the second term, then multiply it to get to the third term, and multiply it again to get to the fourth term.
So similarly to when we did this with arithmetic, I know I'm going to have 2 times r times r times r equals my negative 54. Could you use that to figure out what r is? Take a moment, see if you can get it. It looks like the common ratio r comes out to negative 3. So when I multiply 2 by negative 3, I get negative 6 for the second term, multiply by negative 3 again to get 18 for the third term, and then to verify, I multiplied that by negative 3 and got negative 54, just like the fourth term. So it's cool to see that when that common ratio r is negative, our terms in our sequence alternate sign. So we started with positive 2, then negative 6, positive 18, then negative 54.